All right, I'm going to go ahead and get us started. Welcome everyone to the UFS webinar. This webinar is hosted by the National Weather Service Office of Science and Technology Integration. The goal of this webinar series is to enhance communication, share advancements in all aspects of the UFS in both research and operational settings. My name is Alex Alder, and I'm here to help coordinate and deliver the webinar. Feel free to contact us at OSTI if you have any comments or suggestions. Also, if you have any recommendations for speakers that you'd like to have present this webinar, you can email your recommendations to us at ufs.modeling@noaa.gov, and we will take your suggestions into consideration. Due to the high number of attendees, you'll be in listen-only mode during the event. You will not be able to unmute. If you have questions now or during the event, please submit them on the Google document that will be provided in the chat box shortly. Presentations will last about 30 minutes, and there will be a few minutes of Q&A at the end. And again, just type your questions into the Google Documents during the presentation. For today's webinar, we'll hear about the origin, structure, and tracks of the monsoon onset vortex, integrating theory and predictability studies using the UFS for early season impacts on the monsoon by Mr. Shreyas Diwali with North Carolina State University in UCAR. Shreyas Diwali is recipient of the NOAA Weather Program Office Innovation for Next Generation Scientists, or WINGS Fellowship, and a PhD candidate at the Department of Marine, Earth, and Atmospheric Sciences at North Carolina State University. His PhD research is on the monsoon onset vortex, MOV, which is a synoptic weather system that forms in the Arabian Sea in some years during the onset of the Indian summer monsoon. He studies the origin, structure, and predictability of the MOV in reanalysis data, satellite observations, and numerical models such as the WRF and the UFS. Shreyas is also a recipient of the 2024 John S. Irwin Award for Scientific Excellence from the Department of Marine, Earth, and Atmospheric Sciences at North Carolina State University. I'm going to turn it over to Shreyas to give his presentation.
Yeah, I hope my screen is visible.
I just sent you the confirmation. It looks like it's loaded. Yes, we can see your slides now.
Okay. And all right. Let me know in case there is a break in my audio, because Wi-Fi here is not very strong. So, okay, with that, I'll get started. So my topic is on the origin, structure, and tracks of the monsoon onset vortex, and I'll introduction of this topic, and then we'll go on to the results. So to ensure that everyone is on the same page, I have structured my presentation with first few slides focusing on the background and introduction, and then what is the usefulness of the study, and then we'll move on to data and results, and then summarize the findings. Okay, so introduction and background. So the images here show an overview of the Indian summer monsoon circulation. So it extends from June to September, and you have some salient features of this, which is your masculine high in the southern hemisphere, which is your high pressure region in the subtropical Indian Ocean. And that gives you a strong cross equatorial flow, which after crossing the equator becomes the Somali jet. And your Somali jet is a low-level westerly jet at 850 HPA. It is also known as Finlatter's jet, and Somali jet because it is off the coast of Somalia in Eastern Africa. And this is present during the all 4 months of the summer monsoon from June to September. Then you have tropical easterly jet at the upper levels, and this is the outflow from the Tibetan high. So this is at 150 to 200 millibars levels. Then after this, you have, these are the main features. So then comes the question, what exactly is the onset vortex of the monsoon? So as the name suggests, it is a vortex or a low pressure system which forms during the onset phase of the monsoon. And during the monsoon, there is strong vertical wind shear over the Arabian Sea. This is because, we saw in the previous slides, there are strong low-level westerlies and upper-level easterlies. And that's why tropical cyclogenesis is rare during the core monsoon months of July and August. But during the onset phase of the monsoon, which is typically in late May or early June, a vortex or a low pressure system forms in the Arabian Sea in about 60% of the years. And this vortex is termed as the monsoon onset vortex. And this is a synoptic scale feature which is part of the large scale monsoon circulation. And recent example is Cyclone Biperjoy in the Arabian Sea here. Just give me just a few seconds break. There is some disturbance, so I'll just refix my headphones here. Okay. Yeah, so this is an example of Cyclone Biperjoy, which was formed in the Arabian Sea last year. And this is from June 2023. So the onset vortex most often goes on to intensify into a tropical cyclone. So, this was an example from last year. And this is a Hofmöller diagram, which gives a more broader context of the MOV. So y-axis is latitude, x-axis is your months, and then your contours denote your 850 HPA zonal wind, and colors denote the precipitation. So what we see is from June onwards, there is a northward shift of your seasonal precipitation, and this is accompanied by this coincides with the rapid increase of your zonal wind. So, and when these two are, when the precipitation is shifting north and your zonal wind speed is ramping up, that's when the onset vortex of the monsoon or the MOV forms. So the orange dot here represents the median location of MOV formation, which is in the first week of June. So what is the usefulness of this study? Two main reasons. First is, it affects the onset of the monsoon, and second is socioeconomic impact. So when I say it affect the onset of the monsoon, so either the onset vortex, if it forms and moves parallel to the coastline of India, then south of the vortex you will have strong westerlies from the Arabian Sea, and that can bring in the monsoon early over the west coast of India. But if the onset vortex forms and moves in a westerly or northwesterly direction towards, say, Oman or the Gulf of Oman, or towards the Middle East, then that can drag your moisture flow and the Somali jet towards itself, and there is anomalously reduced moisture transport over the Indian region, and that results in less rainfall, or it even delays the advancement of monsoon over parts of the Indian subcontinent. So, the onset vortex most often becomes a tropical cyclone, and they can affect your climatological wind pattern on a synoptic or subseasonal scale. And the impacts of it can last, even after the vortex has dissipated. Like they may last for up to a week or two after the vortex itself has dissipated. And the second is socioeconomic impacts. So because most of the MOVs, like around 80% of them, go on to become tropical cyclones, and the coastline bordering the Arabian Sea is pretty densely populated. So these are destructive from life. They have caused a lot of fatalities in the past. With in 2007 there was Super Cyclone Gonu, which became a Cat 4 bordering Cat 5 intensity hurricane, and then there even in 2010 there was a very severe cyclone Fet. That also was almost a Category 3 intensity hurricane. So there have been very powerful storms resulting from the intensification of the onset vortex. And of course, this Arabian Sea region is a marine trade route. So you have a lot of marine trade that happens, especially regarding the oil from the Middle East. So that happens along the Arabian Sea waters, and any severe weather disturbance in that basin is it's gonna hamper, it's gonna have some economic impacts as well. Okay, so here's a quick summary of what previous studies have looked at for the onset vortex of the monsoon. So some studies have shown that the Somali jet itself is barotropically unstable. So the barotropic instability of the Somali jet gives rise to the vortex. And other subsequent studies have looked at dry dynamics using idealized models with two atmospheric layers. So they have looked at dry barotropic baroclinic instabilities of the basic state. And then some studies have looked at how is the synoptic environment in the Arabian Sea during the onset vortex. So there is the Arabian Sea mini warm pool, which is the warmest part of the Arabian Sea basin, which is in the southeastern part of the Arabian Sea. And that has SSTs greater than 30.5 degrees Celsius. So studies have shown that onset vortex can form in that particular region of the Arabian Sea. While some studies have looked at the positioning of Somali Jet and the east-west shear zone. So this shear zone is basically you have westerlies to the south and easterlies to the north. So there is a natural cyclonic shear in that particular region. So that may be responsible for formation of onset vortex. So that's what some studies have looked at, but mainly the mechanism governing the formation and growth of the onset vortex is understudied. And no previous studies have focused on predictability of the onset vortex and associated impacts on the early season monsoon rainfall in over short to medium range forecast in global models. So that's where my research comes into play. And for this, the data I'll be using is data from the UFS S2S prototypes, which is subseasonal to seasonal prototypes. And I'm comparing the results from P5, P6, and P8, just prototype 5, 6, and 8. And they have a grid spacing of 25 kilometers, and there are reforecast of all these prototypes from April 2011 to March 2018. And they are initialized on 1st and 15th of each month, and each run generates 35-day forecast. And for validation purposes, atmospheric fields, I'm comparing it with ERA 5. The MOV tracks, I'm comparing it with JTWC best track data. And the rainfall, I'm comparing it with GPM iMerge precipitation. So these are some of the fields, that I'll be analyzing. And this is more like a case study of 3 cases and some large-scale features of the monsoon in the UFS. Okay, so first we'll have a look at large-scale features of the monsoon. So I wanted to check, does the UFS capture, some large-scale rainfall patterns and some correlations correctly? So there is one metric known as the Somali Jet Index. It was developed by Bill Boos and Kerry Emanuel in 2009. And it is basically, the strength of the Somali Jet at 850 HPA. So the mathematical formula for that is, given in blue here, which is the square root of y is the spatial mean kinetic energy of 850 HPA horizontal wind averaged over the Arabian Sea coordinates. And studies have shown, various past studies have shown that if your Somali Jet is stronger than normal, then the rainfall received over the west coast and central parts of India is above normal. So stronger 850 HPA winds are directly related to above normal rainfall over west coast and central parts of India. So one of my objectives was to check whether this large-scale weather pattern, how well is it captured in the UFS. So the figure here is comparing the results from P5, P6, P8, and observations. So top left panel is the plot from P5, top right is P6, bottom left is P8, and bottom right is ERA 5 and GPM. So precipitation is from GPM, winds are from ERA 5. And this basically indicates the anomalous rainfall in millimeters per day for 1 standard deviation increase of Somali Jet Index. So if your intensity of Somali Jet is higher by a magnitude of 1 standard deviation compared to its normal climatology, then the colors shown in these plots show what is the anomalous increase in rainfall proportion, corresponding to that increase in Somali Jet. And the black hatches denote the regions which are statistically significant at 95% confidence level. And for this analysis, since I'm looking only on the early part of the monsoon, I have used the UFS runs initialized on June 15. The reason I didn't choose the runs initialized on June 1, because monsoon season is technically it's from 1st June to 30th of September. But here I've not chosen the run initialized on June 1 because those are likely to have the impact of the onset vortex itself. So to just see how the UFS performs without the onset vortex, I've used the runs initialized on June 15th. And the main takeaway from this is, each prototype roughly, captures the spatial pattern of the relationship quite well. but it underestimates the rainfall amount. So in observations, if you see, the red shades are much darker. So the anomalous increase in rainfall for one standard deviation of jet index is much higher in observations. UFS does capture this pattern well, like P8 shows the increase in rainfall over the Arabian Sea region, while the P5 showing good increase in central parts of India. So some prototypes, they capture certain features well. Overall, all three prototypes do reasonably well, but they underestimate the increase in rainfall amount. Okay, next part of the results is I'll be showing you the three case studies. So, the S2S prototypes of the UFS are, we have the data from 2011 to 2018. And during this period, we had three MOVs which had formed in the years 2011, 2014, and 2015. So I'll be comparing the tracks of the MOVs as well as, some structural components like the potential vorticity and diabatic heating profiles of these MOVs in the UFS versus observations. I also be comparing the subseasonal impact on monsoon precipitation as well as checking the metric of Somali jet index. So how does it compare in the UFS and in ERA 5? And I've used the runs initialized on June 1 in this case because all the MOVs have formed within the first 10 days of June. So June 1 was run of the UFS was chosen to study these three cases. And the way in which I've calculated the diabatic heating and PV profiles is summarized here. First is I've identified the MOV center at 850 HPA. Reason of 850 HPA because Somali jet at 850 HPA is linked to the formation of the MOV, so I've chosen that particular level. And then I've calculated diabatic heating given by the total derivative of potential temperature. And I've averaged the profile of diabatic heating and potential vorticity from T minus 12 to T plus 12 hours, where T0 is your time of MOV formation. And I've also averaged it spatially 2 degrees in latitude and longitude each from the MOV center. And then compared the vertical profiles of diabatic heating and potential vorticity between UFS and ERA 5. Okay, so now let's look at the cases. The first we look at 2015. So this case was the best predicted across, in comparing all three cases. This particular case was the predicted quite well by the UFS. So the observations say that the MOV has formed on June 6, and all three prototypes forecast the MOV to develop or to form on June 6 itself, which is quite good. And this is at a lead time of around 5 days because the run is initialized on June 1. And the color code here is kept it same for all figures subsequently. That is, your black is your JTWC track, and then your orange is your blue is P5, orange is P6, and green is P8. The three different prototypes of the UFS. And what we see that track in P5 is different because the MOV follows a more northerly track here, while P8 shows the best matching track when it compared with observations. And structurally speaking, there are quite some details here written here. So in ERA 5, what we observe is the onset vortex forms by a vertical alignment of a lower tropospheric and a mid tropospheric vorticity maxima. So when those two vortices get vertically aligned, that's when the onset vortex develops. And we have identified the threshold of the onset vortex to have a minimum intensity of tropical depression. So that is the wind threshold criteria that we have defined the onset vortex to be. And structurally, UFS also shows the onset vortex to be a cold core vortex. But in P5, the mechanism of formation is slightly different. It is from a top to down development of a mid-level vortex. But overall, I think P8 performs the best for this particular case. And next is analysis of the Somali jet index. So this particular metric, this is a time series of the Somali jet index from June 1 till June 14. It's a 2-week forecast. And we can see, again, black is your ERA 5, blue is P5, orange is P6, green is P8. And these are denotes your correlation coefficient. So all three prototypes have a good correlation of this particular index, and specifically P8, the magnitude of the green line here kind of matches with black line even, in your second week of June, second week of forecast. So maybe if you get the track of the onset vortex correct, then your Somali jet index is also kind of forecasted reasonably well. And initially as well, the dots here denote the day when the onset vortex formed in those respective prototypes and ERA 5. So before the formation as well, the three prototypes are in reasonable agreement with ERA 5. So that was good. One thing to notice, this particular onset vortex was influenced by a strong amplitude of the Madden-Julian oscillation. So the MJO was in phase 2, and phase 2 is over the Indian Ocean. And MJO, studies have shown that P8 has a better forecast of MJO compared to the other prototypes. So this could possibly be one of the factors why P8 has a good forecast of the intensity and track of this particular onset vortex. And then what is the impact on rainfall? So this is the rainfall difference between UFS and ERA 5. So blue is where UFS shows a strong or higher rainfall or wet bias here. Red is where it's a dry bias in the UFS. So in P5 we saw a couple of slides earlier that the track of the onset vortex was much northerly, while the observations had a northwesterly to westerly track, and that is reflected in your rainfall. So one key feature here is if you get your onset vortex track reasonably well, then the rainfall bias over land is the least. So that is what we see, especially in the west coast region of India. P8 has the least precipitation bias. So the precipitation difference between UFS and GPM is the least in P8. And there are some heavy rainfall regions in the equatorial Indian Ocean, which the UFS is not capturing. But when it comes to the MOV, I think P8 performs the best when it comes to rainfall. And then this is the structure of the onset vortex. Here again, the color code is the same. This is the figure on the left is the potential vorticity, vertical profile of potential vorticity. Figure on the right is vertical profile of the diabatic heating. And some subtle differences like PV maxima in UFS is located slightly higher than that in ERA 5. But the key takeaway here is if your potential vorticity and diabatic heating profiles are matching in your UFS and ERA 5, then probably your intensity of the onset vortex as well as your track is predicted well. So these two parameters could be, if you forecast the diabatic processes well, then it could result in a higher forecast accuracy. And another feature to note here is there is diabatic cooling in the UFS above 150 HPA. So like in your lower stratosphere, you have diabatic cooling in the UFS, which is not seen in ERA 5. And I think this feature is consistent across all three cases that I analyzed. And some subtle differences are like high diabatic heating in P6. So the orange line here is much higher in magnitude than the black line here, but the P magnitude is lower, at least in the mid levels. So this is something which needs to be explored further. Why you don't have high PV in spite of a very high diabatic heating in P6. Okay, and then next case is 2014. So we have observations show the black line, the actual track of the MOV. It formed on June 8, which is like a lead time of 7 days for the UFS run initialized on June 1. In P5, the MOV forms on the same day as observations, but its intensity is very weak, and that's why the strong southwesterlies of the monsoon advect the weak vortex eastwards. That is what is seen here, and it forms here and then moves away eastwards and dissipates off the coast. In P6, the vortex forms a day and a half prior to observations in the UFS, and it forms at a much southeasterly location compared to observations. While P8 is an interesting case here, no vortex develops. There is no surface level wind circulation or no pressure drop. And your mid-level, if we analyze the differences, in the wind circulations in P8, what we see that there exists a mid-level vortex attributed to diabatic generation, but there is cyclonic circulation at mid levels, and that never descends down to the surface. So there is no surface low pressure or surface tropical depression seen in P8, and that's why there is no MOV that forms in P8. And structurally, it is a cold core vortex in in UFS as well as in observations. So P8 has shown, even though the vortex is not forming in P8, the Somali jet index is predicted quite well. So, correlation is 0.95, which is very high. And the magnitude of the jet index is also matching with ERA 5. So your large scale component of the monsoon, which is your Somali jet, its amplitude and its variation with time is predicted well in P8, but still the onset vortex doesn't form. So probably this tells us that you need to resolve or predict convection better, or the diabatic processes better, in order to get the forecast of onset vortex correct. And I checked the differences as well on how convection evolves in P8 in 2014, and we realized that spatially there is a different structure of convection in P8 as compared to observations, and that probably results in your onset vortex not developing in P8, while in observations convection manages to get clustered around a center, and then a tropical depression forms there. So instead of getting your large scale features right, if you don't get the mesoscale convective features correct, then you may miss out on predicting the onset vortex. And impacts on rainfall, I think P8 has missed out on the onset vortex. So the difference in rainfall, or the bias in rainfall over land, is likely to be high. That's what we see. P5 also has a wet bias here near the coast, because the onset vortex was weak and it dissipates off the coast and probably spreading the rainfall across the coastal regions. P6 has the least rainfall bias over land. And that is the main takeaway from here. And structurally as well, P5 and P6, ERA 5 clearly shows two maxima in the potential vorticity, one around 550 and the other around 750 HPA. But in P6 also shows somewhat two maxima in the PV. But overall PV magnitude is higher in P6, and diabatic heating is also high, but max PV is not very high in P6 compared to ERA 5. And in P5, the vortex was weaker, so your PV profile is also lesser in magnitude. Your diabatic heating is also less in P5, so that is kind of what you expect. So, and again, UFS shows diabatic cooling above 150 HPA, which is not seen in ERA 5. So that is one feature which we see across all three cases. And this is the last case. So here, the onset vortex has formed on June 9, which is a lead time of around 8 days for the UFS run, which is initialized on June 1. And this particular case was not predicted well by any of the three prototypes, especially when it came to the day of formation, because in P5, of course, the track is completely different as seen in the blue line here. But the onset vortex has formed around 5.5 days prior to observations. While in P6, the onset vortex has formed 4 days prior to observations, but the track in P6 is somewhat matching with ERA 5, or somewhat matching with the JTWC best track data. While in P8, the onset vortex is weak and it moves over land. But here again, it has formed 5 days prior to observations. And why so much difference? Probably it has to do with you not getting your Somali jet index correct. And this in turn is also dependent possibly on initial conditions, because here, from day 2 of the forecast itself, there are large differences between what ERA 5 shows and what the three prototypes of the UFS show. The correlation also is quite weak in all three, especially P5, the correlation is negative here. And I checked the evolution of various features, and what we see that on June 1, which is your day 1 of the forecast, there itself you have a lot of differences in the OLR and precipitation fields. So probably it may be, it's my hypothesis, it may be related to your initial conditions, some role of initial conditions, because day 1 itself, your UFS starts differing from observations by a quite, spatial pattern also of rainfall, and convection is quite different. So it may have some role of initial conditions for such differences in forecast on day 1 itself. And not getting the Somali jet index correct and not getting the timing and track of MOV correct, that has implications on your rainfall on sub-seasonal scale. So like this is a 2-week rainfall again, June 1 to June 14, and we see strong differences in rainfall. Rainfall difference in UFS and GPM is quite high in P5, P6, and P8 as well. You can see P5 has a very strong dry bias in the northern parts of West Coast and northeastern part of the Arabian Sea. P6 has a strong wet bias along the West Coast, and P8 has a very strong wet bias along the coast. So if you don't get these features correct, then your subseasonal scale rainfall is likely to be different in the forecast as compared to observations. And looking at the structure, the profile, we see that PV maxima in the UFS slightly higher than ERA 5, and this may be related to the way convection develops here. And in P5, surprisingly, PV magnitude is kind of matching in the upper troposphere and very lower tropospheric regions. But two PV maxima are not clearly seen. So structurally, the PV profile differs from ERA 5 in terms of showing two maxima in the PV. And one interesting feature is diabatic heating magnitude doesn't match with PV amplitude. So high potential vorticity in P5 and P6 compared to your ERA 5 is likely not due to diabatic effects, because if you see the diabatic heating profile, then P5 and P6 have a much lesser magnitude compared to ERA 5. So the high PV in P5 and P6 may be due to some other effects, which is yet to be explored. And your peak diabatic heating in P6 is slightly lower than ERA 5. So those are some subtle structural differences. But again, there is diabatic cooling in the UFS above 150. So that feature is like consistent across all three cases. And ERA 5 doesn't show this diabatic cooling. And summarizing all of this, what are the key takeaways here? So Somali Jet Index is a useful metric for studying early season monsoon rainfall variability. And stronger Somali jet leads to heavier rainfall for West Coast and central parts of India. So this was established in past literature. And the UFS also captures this relationship well, although it underestimates the anomalous increase in rainfall corresponding to the anomalous increase in the Somali jet intensity. And the Somali Jet Index is predicted well in 2014 and 2015, but the onset vortex doesn't develop in prototype 8 in 2014. So possibly it is because mesoscale convective features processes are important, and they need to be captured well for to get the MOV forecast correct. And these findings are similar to some of my earlier studies, which has shown that the diabatic processes are the main factors for MOV formation. So that's one reason why I've checked the potential vorticity and diabatic heating profiles, because our studies have shown that diabatic processes contribute the most when it comes to the formation of the MOV. And the dry instabilities are not sufficient for the MOV formation. So it's important to get the mesoscale convective features correct. And three prototypes have forecasted the 2015 MOV well, with forecast matching well with observations. And PV and diabatic effects are forecasted with P8. So this can be important for MOV forecasting. So if you get these features right, then your forecast of the onset vortex is correct. And 2011 case was not well forecasted, possibly because of differences in initial conditions. But overall, I think for these three cases, P6 and P8 perform better than P5. And I also checked the UFS runs initialized on May 15. So this gives like a lead time of more than 2 weeks, close to 3 weeks. But the MOVs are not predicted by the UFS at such a long lead time. So that's why I've analyzed, I could analyze only from the runs initialized on June 1. And of course, a caveat here is, these are deterministic runs, not ensemble runs. So these are just based on a single forecast for all the years. And what is the usefulness of this study for S2S prediction? So the onset vortex can be treated as an extreme event in the context of monsoon onset and early season monsoon rainfall, because onset vortex is like a tropical depression, often intensifying into a tropical cyclone or hurricane intensity. And this study also highlights the importance of capturing mesoscale convective features for accurate subseasonal forecast. And this particular rationale can also be applicable to tropical cyclones forming worldwide. If you get the convective features forecasted well, then your forecast of the tropical cyclone or hurricane is likely to be, it's possibly likely to be more accurate. And another takeaway from this is the Somali Jet Index is an important parameter which influences rainfall variability on a S2S scale. And the winds, 850 HPA winds, are also incorporated in the calculation of other indices such as the boreal summer intra-seasonal oscillation. So getting Somali Jet Index prediction correct is also likely to impact the forecast of other monsoonal indices. And of course, if you get the forecast better for tropical or monsoonal regions, then it may overall result in better forecast for mid latitudes as well, because tropical convection is also impacts mid latitude weather through teleconnections. With that, I'd like to take any questions. Thank you.
Thank you so much. I'm putting the question document into the chat one more time, and then I'll switch over to my screen and share that document as well. Are you able to see the questions on there? There's one so far.
Yeah, I just. That's a pretty interesting point made here. So I have not looked into relationships between Somali Jet Index and the West African monsoon, but it will definitely be worth exploring. So yeah, thanks a lot for sharing that. I'll have a look at it.
We'll give it just another minute to see if anyone has some questions. I see some people popping in and out of the document. All right. Well, thank you so much, and we'll see you next time we have